Shall I start? Yep. Okay. All right. All right. Afternoon, everyone. I hope you enjoyed your lunch. The presentation that I'm going to show you has changed quite a lot from the one that's in the book there, so it'll pay to go to the Black Hat site and download the latest copy along with the code examples. In essence, what we're talking about are local attacks against Win32 applications that implement a GUI thread or a message handler. It's widely become known as the shadow attacks and involves sending exploitable messages to vulnerable applications. Just ignore that. All right, before I start discussing details, I just want to talk a little bit about how to put the problem into context. When the first real shadow attack became public back in 2002 with the WM timer message, it was not really taken that seriously as a vulnerability. It was more of a novelty. This is even by Microsoft themselves. If we look at the Windows operating system historically, it has not really been considered secure enough to be put inside highly protected networks, while other operating systems have already gone through the security vulnerability discovery phase. This was something new to Windows. And like any new system, it had holes big enough to drive a bus through. Historically, secure networks were protected largely by limiting the use of connected computers to trusted employees. And workstations were built using truly secure and tested builds and stripped down hardware to prevent data theft. All right. Technical difficulties mean that I can't see the slides here, but that's all right. Now, like most new exploitation methods, shadow attacks are maturing, and it is now acknowledged that they no longer affect only the WM timer message. The scope of the problem is widening. We're now starting to see some very solid moves towards security by Microsoft. We've got patch management, built-in firewalling, and of course XP Service Pack 2. Now, with this advance in Windows security, there are now more and more Windows machines inside secure networks, and as time goes by, there will be more and more, along with the more trusted employees with access to these. So what's to come? Shadow attacks will continue to widen in scope, and during the presentation we will discuss and demonstrate some of the directions in which these are heading. Secure networks will still have a large number of untrusted employees, if not more than before, and employee turnaround will continue to rise. It will happen at some stage that the Windows operating system will be considered secure enough to be deployed everywhere throughout secure networks. The restrictions put in place on the workstations will be considered secure enough to control access to the network and data, as well as restricting the privileges and actions that employees can take. Now, shadow attacks affect more than just the core operating system, and they affect more than just Microsoft products. Any third-party application service running with elevated privileges may be vulnerable to some kind of exploitation. This means that even if Microsoft patched every vulnerable instance in their products, workstations running the Windows operating system may still be vulnerable to privilege elevation attacks. It is possible that Microsoft will apply a fix to the core of the problem, the messaging system, but this is very unlikely, and even so, it wouldn't be ready anytime soon. So in a real-world environment, how can shadow attacks affect you? Okay, well, privilege escalation is the major impact of these attacks, and in general scope, the most important. Currently, they are restricted to local elevation attacks. This, of course, includes remote desktops, Citrix, VNC, stuff like that, as well as the possibility of worms and other Trojans utilizing these attacks to increase their access to a system. Commonly, programs such as personal firewalls, antivirus systems, and other monitoring software run with elevated writes, and most of these tested have been found vulnerable to attack. Now, a successful attack could allow untrusted users to elevate their privileges to a higher level, allowing them to install malicious programs such as keyloggers, sniffers, and remote access software. Okay, so what can an attacker do? Now, depending on the target application, an attacker may be able to do a number of things. Most obvious is what we just discussed, the privilege escalation, privilege elevation. If a target application is running with elevated rights, normally system rights, then an attacker may be able to gain access to those rights, open a command shell, etc., etc. Since all Windows include default handling for WM close, WM quit, destroy, etc., messages like that, It is possible for an unprivileged user to shut down some applications. Now, this can become important if a user is able to shut down antivirus software, firewall software, monitoring software, or other software that is in use to restrict what the user is able to do. Other attacks could involve the manipulation of controls to allow access to application areas that should normally be denied. We're talking about thick clients here. If a user is able to send an enable message to a disabled button, menu, toolbar, then they may be able to gain access to areas of the application that they shouldn't be able to. If data from user input or GUI text is used insecurely, it could lead to SQL injection attacks and file manipulation or textbook buffer overflows. Now, the Windows operating system uses a mechanism known as Windows messaging to communicate events such as user input, excuse me, system notification, and control information between windows. Unlike the old days when an application would stop and wait for user input, Windows messaging allows an application to process input only when there is input waiting for the application. Each window created on the desktop has a unique window handle to identify it within the system. And messages are passed to the system, which in turn directs the messages to the appropriate window identified by its window handle. The window then processes the message depending on how it was sent and what parameters it was sent to. Every control, such as a text box, a list box, or a form, is derived from the base window class. So throughout this presentation, when I'm talking about a window, I'm referring to any type of GUI control. Now, the problem with this method of sending messages is that the operating system allows any user to send messages to any application. And in most cases, the target application will blindly accept these messages and act on them accordingly. So by exploiting knowing weaknesses in the messaging system, an attacker can manipulate applications for an arbitrary advantage. Okay, so how does a message get from point A to point B? Now, there are two main API calls used to pass messages to Windows and various sub-messages underneath these. All the functions pass the message to the system, which in turn passes it on to the appropriate place. Postmessage and its related functions pass the message data to the message queue of the thread that owns the destination window. The sending application then continues executing without awaiting a response. A thread's message loop constantly polls the message queue, removing and dispatching any messages to the appropriate window procedure for the window identified by the unique window handle passed through the API function. The send message family of functions passes the message directly to the window procedure of the target window. And after the window procedure processes the message, processes the message and returns, the sending application then continues execution. The window procedure is where the message contents are processed. It is in this function where the decision is made based on the message type to handle the message or ignore it and pass it up the handler chain. Every window has a window procedure, which is derived from the base window procedure for the class of the control. Every thread which uses a GDI function has a message queue, and every thread that creates a window has a message queue. Now, we need to keep this in mind when talking about what applications are vulnerable to these attacks. Some applications or services which do not normally display a window can be enticed to create one, which may lead to the exploitation of the service. Of course, one that really springs to mind is if you go net send and a message box pops up with a message, that message box is then created by the service, the messenger service. Your print service, when you have a printer error, the message box that pops up, it's owned by system, the printer service. So to help with the understanding of how a message becomes exploitable, I've broken them down to three categories. Now, a type 1 message correctly marshals the data and behaves as it was designed to. These messages can be used to pass data into a target application's memory space. An example of this would be the WM set text message. The pointer to the text string is correctly marshaled to the receiving application, and the window text or caption of the receiver is set accordingly. A type 2 message does not need any marshalling. The data that is passed is used directly, and may result in the setting of a control's properties. These type of messages can be can be exploitable in some situations. If you think about the WM timer message, the pointer that is passed is not marshaled, doesn't need to be marshaled, but it was still exploitable. Now, a type 3 message can be used to overwrite arbitrary memory locations in the target application. It does not go through the marshalling process, but it should. A value is passed as an offset to a data structure, and because it is not marshaled, it allows us to control the memory address that the target application accesses. Okay, so what is message marshalling? Message marshalling is the process of a system taking message parameters from one thread and passing them to another. Generally, messages are passed between the same application, so memory accessing is not a problem. But when messages are passed from one application to another, the data needs to be modified so that the memory address specified is valid in the receiving application. Any message with a value less than WM user is marshaled automatically by the system. These are system-defined messages, and therefore the system is aware of what the parameters are and how they should be marshaled. Not surprisingly, though, there are a large number of messages that are not marshaled correctly. All of the messages affecting or used by the new common controls, the list view, the tab view, etc., they all reside above WM user, and therefore most of them can be used for arbitrary memory overwrite in one way or another. For messages with an ID less than WM user, marshalling depends on the function of the message. If the message is passing a numeric value that is to be used directly, then no marshalling is required, a type 2 message. But if the message is passing a block of data, such as a text string, the block of data and the relevant pointer need to be managed so that the receiving application can access the data. As you can see here, if the parameter is used directly, as in the WM timer message, no marshalling is required. Whereas the WM set text message, the data from the sending application needs to be put somewhere so that it's valid in the receiving application's memory space. So where does it go? Okay. The GDI shared handle table is a block of memory that is shared between all GUI threads. This table holds the handles of all opened objects from any GUI thread and has enough space for 4,000 GDI table entries. A pointer to this location can be found in the process environment block at 7FFDF094. Now, 60,000 bytes above this address is the start of the process mapped heap. It is in this heap block that the system marshals the message data to. Now, because every GUI thread has this memory mapped into their address space, every GUI application is then able to access this space to access the data. Sorry. Now, what the system does is it copies the data from the sending application into this address space, updates the pointer, and passes that to the receiving application. Now, every GUI thread has this memory mapped into its address space, but at a different base location. But the actual data remains at the same offset within the heap. So the process mapped heap appears to be mapped at a static location per application, allowing us to calculate a static offset between two applications. So by locating the data in one application's process mapped heap, we know the exact location in another application. This removes any guesswork involved in getting data into a target application and allows for the exploitation of more complicated messages. So as we can see here on the attacking application, the mapped heap base is at 4,900,000 something or other, whereas in the target applications it's 53 blah blah blah. So the static difference between that is A00000. So if we know that our data is at 5238CO in our application, by adding the A0000, it'll give us the exact location in the target application. Okay, so we'll come back to the process mapped heap shortly. But first I'll mention some very brief points on shellcode. When I'm talking about shellcode, I'm referring to any data that has been used in an exploit. This can range from a structure block to a text string, right through to code that runs a command shell. If the required action is a command prompt window, then the code in most places only has to call the system API. Now, to make it more robust, it could also include code to make sure that the correct DLLs are mapped first by making calls to the load library function. Because the shell code is executed locally, any relocatable addresses can be assigned at runtime before setting the exploit. This removes the need for any address function lookup code that's normally found in remote exploits and allows an attacker to craft an exploit that is completely operating system and service back independent. This course also bypasses protections such as DLL rebasing that was discussed last year. All the APIs used to pass messages have wide character or Unicode equivalents. This means that complete byte arrays can be passed, and in most cases they can contain null values. The setWindowTextW function is a wide character wrapper for the sendMessage API to send the WM set text message. This can be used to set the title caption of windows and is an ideal way to pass our shellcode. Of course, though, the string will be terminated if a wide character null, as shown down here and on that side down there, is in the string. If a wide character null is required in the exploit, though, we can create that in the memory space by using multiple calls to the setWindowTextW message. Multiple calls that use the same address space, multiple calls will use the same address space if the data passed is a smaller length than previously. So this means if we wanted to create that block there, which includes a wide character null in it, we start first by putting the parts after the null, the 3s, and then by making subsequent calls to it, we write each bit backwards until we end up with our complete bytecode structure in the address space containing our wide character nulls. Various methods have been used to try and locate the shellcode for shadow attacks. And while these have all been successful, most of them have downfalls and are not extremely accurate. This guessing of the address technique makes it difficult to exploit messages that require even the simplest of data structures. There have been methods such as brute forcing, arbitrary byte writing, or even arbitrary memory reading. Sorry. All with the same objective of locating the shellcode in an unknown space. Now, Chris Paget noticed that when you create a message box, the data is copied into every application. What I think he was actually seeing was what I described before, the memory space that's mapped into every GUI thread, the process mapped heap. So to use the process mapped heap to locate the exact position of our shellcode, we first need to find the offset between the process mapped heaps in the two applications. For the target application, this can be done by opening the process and reading the address from the PEB. The address is then adjusted to give us the base address of the mapped heap section. Of course, this method requires debug writes and is done on a computer under the attacker's control, just like when creating an exploit for a remote service. The base address for the attacking application can be discovered at runtime by reading the local process environment block and then adjusting the address again. The difference between the two gives us the offset to adjust the shellcode location by, giving us the exact location of our data in the target application. Using setWindowTextW is an ideal way to place our shellcode into the mapped heap. On this graphic, we've shown the setWindowTextW being sent to the target application. Now, this is not necessary, and it's just shown for clarity's sake. We could, in fact, send that message to ourselves to set our caption window. Either way, our data will be placed into the process mapped heap, and it'll be available to any application with a GUI thread. The attacking application can then search locally to locate the data in its mapped heap, and then by adjusting with the offset that we described in the previous slide, we know the exact location of our data in the target application's memory space. So to recap, we've shown that it's now possible to place arbitrary data containing any values into a known location of any application with a thread implementing a message handler. Now this forms the basis for all message attacks going forwards and allows us to exploit messages that require even complex data structures containing pointers. So let's talk about some of the attacks. Now, the callback attack is the classic shadow attack that was made public back in 2002 with the WM timer message. These attacks exploit messages that pass a pointer to a function. The receiving window procedure uses this pointer as the location of a callback function, and therefore execution jumps to the location specified in the message. Microsoft finally acknowledged this was a problem and released a patch to address this issue to prevent the WM timer message from executing callback addresses that were not previously registered. Since then, a number of other messages have been found vulnerable to this type of attack, and it should be realized that any message that implements or uses a callback function may be susceptible to this type of attack. So we've listed here a few messages that accept a callback as a parameter and are easily exploitable, and a few that accept a callback within a structure, which are now also easily exploitable. So the callback attack starts by getting the shellcode into the address space of an application. We know that by using the process map heap, we can place our shellcode into a known location in any target application. The callback message is then sent, passing the location of the shellcode as the callback function pointer, and the target application blindly accepts this, and the shellcode is executed. Not too long ago, Video Marlow released a package under the name of Easy Shadow. It can be found on Security Focus. Excuse me. This allowed him to craft some attacks without the need for locating the shellcode. Now, he realized that the callback function for the em set word break proc ex message took a pointer to a text string as its first parameter. And he noticed that the load library function also took a pointer to a text string for its first parameter. So his attack involved typing or pasting the name of a DLL into a text box and then sending the em set word break proc ex message with the address of the load library function as the callback function. Now, this of course meant that whatever DLL he had typed into the text box was loaded by the application, and any initialization code within the DLL was run. Now, this removed the need to find or write any shellcode into the target application, and is basically the standard return into libc exploitation method. So if we look for any other APIs that fit this mold, two that quickly spring to mind are set unhandled exception filter and system. To exploit the set unhandled exception filter, it would require pasting the shellcode into the text box and then sending the em set word break proc ex message with the address of set unhandled exception filter as the callback function, and then causing an exception in the application, which will then cause our shellcode to be executed. The system API would be much easier to use as a return to libc type exploit method, and would simply involve typing command exe into a text box and then passing the address of the system API as the callback function. Now this is what we've done to exploit the em stream in message. So the em stream in message takes a pointer to an edit stream structure which holds a cookie value and the address of the callback function. Using the set window text W API, we're able to create a valid structure in the process mapped heap and find the exact location of it. So the actual edit stream callback function receives the cookie value as its first parameter. So by building a structure that contains the pointer to our string as the cookie value, and then passing the address of the system API as the callback function, we can cause the rich text box to call system passing our cookie value, which points to our string, to the system API, therefore opening a command shell. Now, the chance of a system application actually having a rich text box is probably about 0. But what we're trying to show here is how it's now possible to exploit exploit messages that require complex data structures, including pointers to themselves. Back in 2003, it was discovered that various Windows messages could be used to write data to an arbitrary location in a target application. The exploitable messages revolved around the use of two different types of message. The first message needed to be a type 2 message that could be used to set the size of some GUI object. The other message needed to be a type 3 message that could be used to pass the address of a data structure that could then be used to overwrite arbitrary bytes in an application. Researchers discovered that the value passed with the LVM getItemRect message was not marshaled and could be used to write a rect structure to arbitrary locations. Now, this was used in conjunction with LVM setColumnWidth function to achieve arbitrary byte writing. By setting the width of the second column of a list view, by setting the width of the first column of a list view, it is possible to have the left member of the rect structure of the second column written to an arbitrary location. So what I've tried to show here is that the yellow bits are the rect structure, the left top, right bottom, and the purple bit is the address that we pass with the getItemRect structure. So by sending these two messages, we're able to write arbitrary bytes to a location of our choosing. So by using multiple calls to these messages, we can write bytes in a sequential manner, causing our shellcode to be written to a location of our choosing. So far, exploit code has been publicly released for the following messages. As can be seen, these type of attacks affect numerous controls, right down to a basic button if the target application is running on Windows XP using extended styles. So by writing arbitrary bytes, we can place our shellcode in a known location. But we could have done that using the process mapped heap, as explained before. So to gain execution control, we need to overwrite some important memory addresses, such as the top-level exception filter. So what can we overwrite? Okay, now the top-level exception filter, or the top-level exception handler, or unhandled exception filter, is commonly used in remote exploits to gain control. So we can use that same method locally. We write our shellcode to a known location, and then by overriding the top-level exception handler pointer with the location of our shellcode, we can causing an exception, we can cause our shellcode to be executed. Now, in some cases, the SEH method may not work. So an attacker can overwrite various other pointers, such as the PEB nunlock pointers under Windows 2000. As with the SEH method, the shellcode is written to a known location in the target this time though, it's in the target application's heap. Now, the PEB lock pointer cannot be overwritten byte by byte because it will be called in between our messages. So what we can do is we can write out the shellcode to a location in the heap that contains the lowest significant word of the original PEB pointer. And then by writing a byte to the third byte of the PEB pointer, 0 will be written to the fourth byte, allowing us once again to gain control in execution. So we send a message to place our shellcode somewhere in the heap that contains, at a location that contains the lowest significant word of the original PEB pointer, and then send a message to overwrite the third byte of the PEB pointer, and once again gaining execution control. Okay, if the SEH method fails and the lock pointers don't exist, it's possible to overwrite the GDI dispatch handler table. This point is the location of a table of functions and can be overwritten in a similar manner as the PEB, with one extra step. Oops, try that again. Okay. The shellcode is first written to a non-writable location, such as up in the PEB. And then a pointer to the shellcode is placed into the heap. Because we can't overwrite the GDI dispatch table byte by byte, we need to use the same method that we used to overwrite the PEB. So the pointer to the shellcode needs to be put into a location containing the lowest significant word. And then we overwrite the GDI dispatch table in the process environment block, and it all jumps around. The application will look up a pointer from our table, which is in the heap, and that points to our shellcode. So the shellcode is then executed again. Now let's see, runtime terminators are very similar to the at-exit pointers on Linux. And they're called from the exit routine on normal or abnormal termination of an application. Do exit calls init term to process the terminator list, calling each terminator function in turn. So by overriding a pointer in the termination table and then sending a WM close message or causing an exception, it is possible to have our shellcode executed. Now, as can be seen here, these are static location pointers that are passed to init term. So by placing the address of our shellcode at, for example, 780.3a.14c, when the application closes or abnormally terminates, it will be run. Now, while we're talking local attacks, for any of you people that do work on remote exploits, these can also be overwritten with remote exploits if the target application then closes. So it's a new pointer or another pointer that can be used to gain execution control. So to recap, we know it's now possible to place our shellcode into a known location. And we have explained how there are multiple ways of having execution passed to our shellcode, either through callback attacks or arbitrary byte writing locations, overrides. Now, just like any of the numerous security vulnerabilities caused by the use of unsafe user-supplied input, input pass-through messages needs to be sanitized and checked before it is used. MSO 3045 proved that even messages that are marshaled correctly may not be safe from exploitable conditions. The buffer overflow in user 32 DLL could be caused by sending a large directory name to a list box through the lbdir message. Sending this attack against the list box and utility manager allowed an attacker to escalate their privileges even though the data was marshaled correctly. Now, writing secure code from Microsoft includes a couple of paragraphs about some dangerous messages. It recommends that before calling any of the getText functions that you can see there, you should check the length of the text string first. Now, what makes these messages a bit different from the other messages is that you can't pass a parameter that restricts the length of the return data. So if you've got a buffer that's only 100 bytes because you're only expecting your tooltip to be 100 bytes long, but an attacker has changed the tooltip length string to 200 bytes, and then you receive it into your buffer, you've of course got a classic buffer overflow. Now, this is really good advice, but as you can see, all these messages, most of these messages reside above WM user, and therefore they can most likely be used for arbitrary byte writing anyway. And this process of requesting the text length, allocating a buffer, and then receiving the text could also open your applications up to race conditions. I mean, what happens if an attacker changes the data between the time of check and the time of use? Classic buffer overflow stuff. Now, Spy++, that's included with Visual Studio, is probably the tool that we've used the most during our research. It allows you to list all the windows that are open, find out all the threads, the processes that own them, and it makes it very easy to discover the window handle of any window and gives you some nice properties of those windows. On Windows 2000, Task Manager doesn't show you what user the application is running under. But if it's running under system process, then it won't allow you to close it using the end process selection. Of course, under Windows XP, Task Manager conveniently displays the user the application is running under. And if you look at that list, you can still see a lot of applications running under system. Now once a target window has been acquired, a message fuzzer can be executed against it. Now message fuzzers work just like any other type of fuzzer. It iterates through a range of messages, sending different types and different lengths of data. Now there are some messages that you want to avoid if you create a fuzzer. Of course you don't want to be sending WM close, WM quit to the target application because it will just close and it won't receive any more of your messages. Now various other messages will also cause exceptions local to the fuzzers as it's trying to marshal invalid data pointers. If you send a WM text passing 1 as the parameter and it tries to marshal that, it will have an invalid access violation. After finding a message that causes some kind of error, it may need to be reverse engineered to determine how and if it can be exploited. Now it's possible for applications to define their own messages for communication, and when some applications do define their own messages, they may be opening themselves up for exploitation. So application programmers need to be aware of the issues arising from arbitrary messages being posted by other applications and users. Now the next three slides discuss a problem we found on the WinHelp32 application. So Utility Manager, when it displayed a tooltip, it would load WinHelp32 as system. So we ran a message fuzzer against WinHelp32, and this is what we found. So we'll kind of try and step through this. Okay, so we ran our fuzzer passing 1 as the parameter, and that first of all calls an exception when WinHelp32 tried to reference memory at 04. So we created a block of 1s up in the process environment block, and we pointed EDI to that block and then continued execution. This then led to another exception where ESI was pointing to 11111111. Okay, now what that told us was that ESI had been loaded with a value from our data block. So originally we were in control of EDI, and we're now in control of ESI. So once again, we pointed ESI to our data block of 1s and continued execution until we came to this first chance exception. And as you can see here on the call stack, EIP has been set to 11111. So if we look back on the call stack, and we can see that what's happened is WinHelp32 has made a call to a double word that is pulled out of a block of memory from ESI. Now, because we controlled ESI, because we controlled EDI, we now control EIP. So this allowed us to create an exploit structure that started off with a block of pointers pointing to the second block, and the second block contained a block of pointers pointing to our shellcode. We could then send the message passing the address of our structure, which EDI would then be set to the address of the pointer 1 block. ESI would be loaded with a value from there, and so ESI would then point to the pointer 2 block, and of course that meant that ESI plus 36 would point to a pointer to our shellcode. Even though there are easier ways to exploit WinHelp32, we thought this was kind of interesting as it was an exploitation of an undocumented message or an application or a custom application message. So another thing that programmers need to be aware of is the default behavior some controls exhibit. For example, controls such as the list box and combo box will by default accept an LBDIR or a CBDIR message to load a directory listing. The attack you can see here is this exploit executed against the list box within Utility Manager. So what this does is it allows any user to send this message to Utility Manager, and it will display a directory listing read as system. System apps that show an about screen with a hyperlink, they may be vulnerable to then loading a browser with system rights. And this could lead to execution of command exe with increased privileges. This is very similar to system applications that invoke the default help handler. The help viewer is loaded as system, and since the viewer contains an IE window, a user can simply browse the local drive and execute command exe once again with system rights. Any system application that allows file loading, saving through the common file dialog is of course opening themselves up to a user just selecting open with command exe and once again obtaining a system level command prompt. We tested one application recently that tried to avoid this problem by using the older file open file dialog type dialog box. Okay, we thought this was quite a good thing because these dialog boxes don't allow you to right mouse click and use the open with context menus. What they do, however, allow you to do is right mouse click, select what's this, and of course that tooltip is loaded by WinHelp32. So WinHelp32 is then loaded as system, and as we just saw previously, WinHelp32 is exportable by itself. Now Cesar Cerrudio has recently publicized a couple of exploits that exploit this scenario using the WM command help message. It's very simple. You send a WM command help message to this dialog here, WinHelp32 will pop up and say, we can't find the help file you specified, would you like to look for it? You go yes, you're then browsing the drive as per here, select open with command exe, you once again got a command level, system level shell. So when we mention shadow attacks, we generally envision these privilege escalation attacks. And while they are privilege escalation, they are only local privilege elevation attacks. They cannot be run through the IWAM user account. So if someone exploits your IIS server, they cannot use one of these attacks to increase their privileges. For an attacker to exploit these attacks, they must either be sitting at the machine or have a remote session such as Citrix Remote Desktop. Based on this, if you think for a moment about what other type of attacks may be possible, there are still many thick clients in use today, mainly around the areas of like accounting packages, content, customer management, etc. So I didn't have time to actually find any exploitable examples. What we've got here is one I created. Now, if a thick client application was programmed in this manner, that it took the user that was selected, asked for their password, and then accepted the password, and then once again took the user from the list and logged you in as that user. If a malicious user was able to change that item, in between that time, they would of course then be logged on with the privileges of the higher level account. So if you write thick client applications at all, you need to be aware that these type of attacks can exist as well. So, the future of Windows GUI attacks, or shadow attacks. As the research furthers into the area of GUI-based attacks, the scope will widen. Attacks will become public that no longer depend on these controls and messages. Exploits will focus on other API calls that are used to manipulate GUI data and window information. We have done some research into this area with the aim of trying to discover if an attacker can use a generic shadow attack to jump from the IWAM user account to system. Currently, though, we are unaware of any vulnerabilities allowing for applications to cross this WinStation desktop boundaries. Although IWAM user can start GUI-based applications, it does not have any access to the interactive system processes, as these all display on WinStation 0. But as long as there are accessible windows running under a higher context, there is the possibility of attack. Now, as any parent knows, children can be a pain. And as any child knows, parents can be controlling. So what happens when a child no longer trusts its parent? What we have here is an example of an API call that affects GUI data that can be used in an insecure way. Now, MSDN states that an application can use the setParent function to set the parent window of a pop-up overlapped or child window. The new parent and the child window must belong to the same application. No. Now, so far we've been unable to exploit this vulnerability in a real-world situation, but that does not mean that it is not exploitable under certain conditions. So we've got here a theoretical attack. Okay, what happens if the exploit becomes the parent of a window or a control? The target application calls getParent to receive its parent, and then it asks its parent for some information. So if an attacking application can become the parent of a control, it can then pass back to the target corrupt data that may cause exploitable situations. Now, we did say we have been unable to exploit this in a real-world situation against system applications. We have, however, been able to exploit this against non-system applications, but there's not much point in exploiting an application you already own. You're only going to become yourself. So this really affects MDI windows, MDI applications, owner-drawn controls. But as research continues, it may come out that there are situations where this API can be used to, once again, gain system controls, system-level access. Every window can store data associated with its application if required. The getProp and setProp API calls can be used to manipulate this information. Now, a window property is usually a pointer to some window-specific data, but it can be any 32-bit value. For example, in an MDI application, the programmer might store a unique ID for each window that corresponds to a record in a database. The problem, once again, is that there are no restrictions on retrieving or setting these values, so any application can set the window property of another application's window. Now, like the setParent vulnerability, we've been unable to exploit any of the core Windows services, but the first third-party application we tested was found vulnerable to this. MFC automatically subclasses all non-MFC derived windows. This is to handle specific activation issues. And what it does is it stores the original window procedure address in a window property. Now, because it's stored in a property, we can set this address to anything we like. And this address is then called in turn when the subclass window procedure is called. So because we can modify this address, we can once again gain execution control. So there have been various discussions around the use of filters to prevent malicious messages from being processed, either through disallowing known unsafe messages or only allowing known safe messages. How do we know which messages are safe? I mean, one of the main problems with this approach is that we don't know which messages are safe. And as we have shown, it's not just messages that can be exploited. So to prevent privilege escalation attacks, no window should be created under the system account. While this helps, the system application will still have created a GUI thread and could still possibly be attacked through messages such as post-thread message. When dropping rights to create a window, it is not enough to just impersonate the currently logged on user. A shellcode can then call revert to self to become system once again. If your application uses its own messages for communication, care needs to be taken to ensure that the message has passed with valid parameters. User input, which is what messages contain, should not be blindly trusted. So if a system service must have an interactive interface, the interface should be started under a lower user account, such as the logged on user, and communication should be done from the service to the GUI using RPC, name pipes, or sockets. This is all documented in MSDN under Tim and Michael Howard's papers. It is possible to prevent any service from loading with interactive abilities by setting the No Interactive Services Registry setting. Doing this, though, will cause a lot of services to not function correctly, and in some cases will cause an error box to be displayed, loaded with system privileges. So above all, awareness is the key, and by knowing what is possible, it allows developers to realize the problems and program their applications with this in mind. In reality, Windows messages and GUI-controlled data are just another attack avenue that needs to be handled safely, similar to input received through network packets or files. Hopefully this presentation has helped you understand the threat and will give you some of the information required to test your applications so that they can be safe from Windows GUI attacks. And either I talk very fast or my friend's watch is slow. But any questions? Okay, the messaging fuzzer is part of the Blackout distribution, so it can be downloaded. What it does, you give it a target handle of a window, and it basically runs through all the, increments, and runs and sends every single message possible to the target window, passing, I think I've got in there, maybe 8 different types of data. It'll pass like 0, 1, 1, 0, 0, 0, 1, 1, a pointer to a large text block, etc. Any other questions? That process mapped heap, yes. Yep. No, but I haven't looked. But yes, it's quite possible. So that process mapped heap is read execute. So when we first saw it, we thought, oh, this is great. We can start writing data that other GUI threads will read, but unfortunately we can't. Sorry? Oh, sorry. The question was inside the process mapped heap if I'd ever seen things like passwords and other sensitive data. So what was that? Yeah. Right. Okay. So the question was, does the process map heap span the desktop boundaries? No. The process map heap, as far as we're aware, is for the desktop that the application is running on. No more questions? One more. Yep. Sorry, could you say that again?
Are you guys doing any research to do automated persistent attacks?
Automated.
Multiple applications running.
Right. So the question was, are we doing any research into persistent attacks against applications? No, but all you're talking about is you're running some sort of Trojan on someone's computer and it constantly polls looking for the title of a vulnerable application. So for example, an attack against one of the personal firewalls, so that when the user opens his firewall, the attack launches. No, but it's completely possible. Yeah. Any other questions? No? Okay, well I hope you enjoyed that.